So today we get to talk about the World Wide Web and HTML. We already talked about this stuff, JavaScript, etc. Right? And this is the primary development environment for the project. And in some senses, one of the primary development environments for software construction worldwide. So to recap, what we have here is really a protocol HTTP, and it started off in version 1.0 as a very simple protocol, sort of a request response protocol. A sample request is from the client to the server, and it looks something like this. You specify the resource on the website that you want to retrieve. So you might say, I don't know, classes CS35L, something like that. And then you specify a protocol, which originally was 1.0. You put any auxiliary information here. Originally, you didn't have to put anything. And then you put an empty line. This is the message from the client server to the server. And then the response from the server back to the client, because we're assuming here we have a bidirectional TCP connection, right? Is going to look something like, there's going to be a header, which is meta information, which will say things like content type and, text, HTML, and a few other bits of information like maybe a timestamp, and etc. And then an empty line, and then the body, which in the original HTTP protocol could be pretty much anything you wanted. There's going to be a length field here that warn you how big the body is. And that was that, right? The client would send a message over a TCP connection. The server would send a response back over the same TCP connection, and then the server would drop, right? So this is an entire connection. I should say TCP, I should say. So in front of this connection, there is all of the lower level protocol involved in TCP in doing a setup, right? That the client doesn't really see because it's just saying, I want to create a connection. That's all responsibility of lower level stuff in the protocol. And over here, we're going to tear down that TCP connection. And again, there'll be a few packets interchanged and all that sort of thing at a lower level. But we don't care about that since we're operating at the higher level connection. Now, although this is a very simple protocol and sort of easy to explain and all that sort of thing, it's got some real efficiency problems. And those efficiency problems have to do with things that we talked about last time. How much throughput can you get out of the system? And what's your latency going to be when you send a request and sort of have to sit and wait for a response to come back? So eventually, after much trial and error, the protocol designers who had been seeing web pages used and perhaps misused and slow and people complaining came up with HTTP2. And this is mostly about efficiency. Trying to make sort of the user interface nicer and faster, and also, place less load on the servers and that sort of thing. So here are some of the ideas that are used in HTTP2. Okay, first off, header compression. The data that I'm circling sort of here and here in the original HTTP was sent just in plain sort of uncompressed form over the internet. And that's easy to debug, and some nice properties of not doing it. It uses less CPU time and all that sort of thing. But the downside of this approach is that as time went on, these headers got bigger and bigger. There's more and more information in the headers, identifying more about what the request is, what the response is, and all that sort of thing. And we're talking, at first it was just, 100 bytes, then 1,000 bytes. Sometimes now it's 10,000 bytes. So it makes sense to compress the headers. But when you're going to do header compression, of course, the client and the server have to agree about what technique is going to be used. And that's part of the HTTP2 protocol, how you agree about how to do header compression. Second major idea was the idea of server push. In the original approach, it was always client pull. Every communication from the server to the client was in response to a client request. You couldn't get anything out of the server except by asking for it. And this made it difficult to build applications where the client sort of gets running commentary from the server, like a stock ticker or an audio server or something like that. Because what the client would have to do constantly is say, has the stock price changed? Has the stock price changed? Has the stock price changed, right? So this avoids polling by the client, because the server can now spontaneously, whenever it wants to, send a response back, even though the client hasn't issued a request, at least not recently. What the client will do at the start, the client will say, okay, I'll accept server spontaneous responses. And then the server is free to send responses of a certain form, even when the client didn't request it. Of course, the client has to be prepared for this and has to sort of know how to interpret the response to a request that it didn't send, but we've got a protocol for that. The third approach for efficiency is perhaps less obvious. It's pipeline. And this isn't like pipes in the shell. This is a different kind of pipelining, although I guess it's a pipe in some sense. Here's the basic idea, right? In the original approach, if time goes this way, what would happen is the client would exchange a few messages back and forth with the server. They'd do a setup, and then it would send a request, and then it'd get a response back, right? And then we do a teardown, right? And if you wanted to, get another web page from the same server, or maybe get an image to fill out the current web page, you do it all over again, right? You do a setup, and you send a request, get a response back, and do a teardown, and do it all over again. So each one of these is a separate TCP connection. Now, in HTTP2, first off, we don't have to tear down the connection each time, right? So we can get rid of this overhead here. We'll go a little bit faster now because we can get the request and the response this way. We keep the connection alive, right? But and that's part of pipelining. But a bigger part is the following. If you do a setup, you can issue several requests to the server simultaneously not simultaneously, you have to do it one at a time, right? You've got to ship the bytes over the TCP connection, but you can ship out, say, 3 requests without waiting for a response. And then get the responses back. The server will get these 3 requests and will decide kind of on its own which responses to send back when, based on its own internal details. It may see, I think I can answer this request first, so it'll issue this response first, right? And then maybe it can handle the first one second, and it'll send that second, right? And then this one it'll do last, right? But the point is that this approach is going to be faster than the old approach: request, response, request, response, request, response, because you're doing three things at once. You've got three requests in the pipeline, sort of waiting to be responded to, and then the responses can come back in any order. Now, there's a downside to this, right? The downside is, first off, the protocol is going to be more complicated, because when you get a response, you won't sort of know that the responses came back in the same order and request, and therefore your browser now has to be able to deal with out-of-order responses, right? That is, you have to sort of have labels on responses corresponding to labels on requests. The requests will be labeled A, B, and C. The responses will come back B, A, and C. And because the responses are labeled, you'll know that, oh, they're out of order. But more importantly, the browser now has to be programmed to sort of display data on the screen, not in the order that you really wanted it to be, but in the order that it actually arrived. Okay? A lot of times this is done by the browser transparently, so you don't have to worry about it. But if you're writing a web application, you're writing code in the client, you're going to have to sometimes deal with responses that are out of order when you're dealing with a busy web server, or with a busy network for that matter. And so you're going to have to sort of take that into account when you write your application. Your application will no longer be a simple sequential program where you kind of call a function to get an answer from a server and get the result back and then keep going. It's going to be more complicated than that. The fourth thing is multiplexing. This one is perhaps a little bit harder to arrange or to describe, but the basic idea here is that we want to set up a single TCP connection. Again, we're trying to avoid that setup, teardown sort of thing for multiple conversations. Or sessions, or whatever you want to call it. One possibility, for example, is this. You have a single physical web server that's servicing multiple sort of web domain, right? So here's your server, right? It's sitting on the network. Here's our network. And it's, say, www.cs.ucla.edu, right? So it'll get a response intended for that, web server, and a request, and it'll send a response back. But the same physical server can also be the server for ECE, right? Because our two departments are so friendly and so cheap, we simply have one web server deal with the two domains, okay? The way that's going to be handled at the protocol level is that the requests now gets extended. Associated with each request is the actual host or domain name that we're interested in. Right? So along with each request comes sort of the idea that, oh, I'm interested in your web server, from the CS department. So our physical web server now knows how to respond to each request. Okay. And what we can now do is have one conversation with the CS department and another conversation with the ECE department from the same web server to the same, client at the same time. Your client can have two browser windows open, one to each domain, and it's really just talking to a single web server with a single TCP connection, even though you think it's two different web servers. There's other reasons why you might want to have multiplexing, but that would be one example. And the protocol allows this sort of thing. And again, the idea is to avoid this sort of set up and tear down overhead. All right. So this is about efficiency. And this protocol became announced in 2015. But there's still one major efficiency or user experience sort of issue here that even HTTP2 doesn't address. And that has to do with the layering that we talked about last time, right? So layering, I mentioned at the bottom, you have the Internet protocol. Above that, you have the transmission control protocol. The Internet protocol is about packets. TCP is about data streams, right? And HTTP 1 and 2 are built atop TCP. And the problem with this approach, from the user's point of view, from a networking point of view, it's nice. It gives you level of the abstraction. It's easy to program, all sorts of good stuff. You can do multiplexing with it. You can do pipelining. You can do server push. It's great, except it has a major problem called the head of the line problem. Right? And the head of the line problem really isn't a problem that comes from HTTP itself. It comes from TCP. TCP's goal is to give you the illusion that you can send packet data in a certain order from point A to point B, and it will arrive as sent, right? Underneath, your packets can get lost and duplicated and all that sort of thing. But at the level of the TCP abstraction, if there's a packet that's lost, TCP arranges to resend it, right? What can happen from a TCP point of view is you have a packet that's lost, the other packets will arrive at the destination, but they won't actually be delivered to your browser, right? So the head of the line problem here looks like this. Here are the packets sent, right? And let's assume they're sent in a time order 1, 2, 3, 4. Packet 2 doesn't get there, right? What the receiver says, what the receiver sees is just packet 1, right? The receiver is not yet given the contents of packets 3 and 4 yet. They're sitting there somewhere in the, in an IO buffer somewhere inside your laptop or something, but your browser doesn't see the packets because you're running TCP. And TCP says, I want to preserve this illusion. I want you to see all the packets in the order that was sent. We don't have packet 2 yet. I'm negotiating. I went back to the sender and said, please send me this packet, and eventually it'll get here and we'll be okay. But in the meantime, all you see is packet 1. Well, suppose this is video. And you're watching, I don't know, Steph Curry trying to sink a three-pointer or something. And all of a sudden, the screen poops out and you can't see whether the basket landed or not. And okay, fine, you missed part of the ball in the air, but this is going to tell you whether or not the shot was made. So in video and other similar real-time applications, TCP is bad. And that's the way the web, has been built for decades. So what HTTP3 attempts to do, well, and in fact does, is it attacks that head of the line problem by not being built atop TCP. It's built atop another protocol called QUIC. You can tell the person who designed this protocol, is good at marketing. But the basic idea is that you can think of this as being kind of like TCP version 2 with UDP. That is, what Quick attempts to do is give you the advantages of TCP, of having the illusion of having data in the proper order. And yet, if you want to, you can say, you know what, it's okay for you to drop packets every now and then, as long as you tell me about it and that sort of thing. So Quick is a more complicated protocol. But for this particular problem, it works pretty well. The browser can see that, you know, a packet was dropped and can see that maybe it'll show up later, but it mostly gets packets in order. All right. So HTTP3 became sort of standard, or, you know, they'd been working on it for a few years, but it finally came out last year. And a lot of browsers are now using it. I would say probably at this point it's the majority, but by no means universal for internet transmissions. And you know, we're seeing it being used for that. Another thing that it did was even more multiplexing, but that goes sort of beyond. Multiplexing turns into a big deal. This sort of thing. You're trying to get multiple conversations between a single client and a single server, so that you can do, for example, audio and video streams and keep them relatively in sync and all that sort of thing. All right, so I've been talking so far about network protocols, mostly. I mean, this is a little bit about the data. Over here, this is really, you know, CS118 stuff. So that you can see where the slowdowns are going to come when you build practical applications with this kind of technology. Any questions before I jump into the software part? Yes. Yes, in theory, it would be forever. In practice, it's usually not forever. But yeah, what you will experience in the worst case is, you know, if somebody pulls the plug on the network, so you're not connected to the network anymore. In that case, your browser simply hangs, right? Waits, you know, maybe you can reboot your machine or kill off the browser or something like that. So usually the network's not that bad. You're on a flaky Wi-Fi or something, and eventually you get some packets and it starts to make progress. But yeah, it can wait for quite some time. Oh no, the idea here is that the server, say, let's talk the server sending, and this is the client, right? So we've sent all 4 packets, and receiver has gotten 3 and 4, and it's gotten 1, but it hasn't gotten 2 because 2 got lost. Okay, all the, you know, this is sort of sitting in the buffer. So, you know, your low-level network driver knows about them, but your browser hasn't seen them yet because the browser says, you know, give me the next piece of data. And we don't know what the next piece of data is. So it's just sitting there buffered. So it's frustrating for the application developer because the data is there. We can see if the basket landed, but, you know, the browser can't be programmed to show the data with a, you know, it can't deal with a missing packet. So that's the real problem with HTTP 1 and 2, or a major problem. Other issues with the protocols? Yes.
So if we allow for some packets to drop, what would the video
That's going to be up to the application. So it could say show a black screen, but that's pretty ugly, right? So what it will sometimes do is pretend that the missing frame isn't there. And so you will see sort of a jump, or it will try to do the timing right. It will show, let's say it's, I don't know, 30 frames per second. It'll show 1 frame for, you know, a 15th of a second, twice as long as it should. So you'll still see a flicker or something like that. But, you know, or it could try to interpolate. It'll try to guess what the missing frame was by seeing 1 and 3. It'll guess the contents of 2 and sort of, you know, there's all sorts of stuff you can do. That's outside the scope of HTTP. That's up to the application. Okay, other comments on the protocol? All right. So next, I want to talk about HTML. This is from HTTP's point of view, completely uninteresting. It's what goes here, right? It's this thing here, right? And HTTP doesn't really care. It's just data. But as someone who's writing the overall application, you're going to care because that data is what's driving what appears on the client screen. So you've already seen, actually, some HTML documents, right? You saw when you were doing the first homework or two, because you had to navigate around an HTML document in Emacs and that sort of thing. So I don't really have to sort of tell you all the details. But first off, as I mentioned before, it's sort of derived from a publishing algorithm, or a publishing format, I should say, SGML. And the philosophy here is that what we want to do with SGML and HTML, to some extent anyway, is we don't want to have a program that you run that specifies how to print a book. We just want to have the content. So the mantra of SGML, which HTML sort of inherits to some extent, is that it's declarative, not imperative. And by this, I mean, imperative is what you're used to in CS31. You're used to writing a program to tell the computer how to do something. So you will write loops and you'll write function calls, and little bits of the program will unfold in perhaps unexpected ways, at least unexpected if you're not an expert, right? That's imperative, right? It's a set of commands to produce a document. You can do it this way. And I've used systems that run this way. But what publishers found when they were trying to interchange documents between, say, Addison, Wesley, and Pearson and that sort of thing, is that imperative is hard to port. Every publisher's system had sort of a different command set. And for them to come up with a portable standard meant they had to agree on what their underlying machines could do. And they have competitive advantages of their various machines. This is sort of hard to port. And for this reason, SGML anyway, is very declarative. So instead, what you have is markup that expresses sort of the document semantics, or the meaning of the document, without saying how to print it, right? Without specifying, printing details. Okay. So instead of an imperative approach, which might look like this, suppose you wanted to, I don't know, print a paragraph. So in the imperative approach, you say, okay, let's space out a half a line, and let's have a temporary indent of, say, two M's, right? An M is a printer's unit that it's the length of a lowercase m and all that sort of thing. And now we'll start off a paragraph here, with some text. And at the end of the paragraph, we'll have another, say, a quarter line space, right? So in effect here, we're writing a little program that says, here's what the printer should do. In a declarative approach, you just say something like this. I have the start of a paragraph, And then here's the contents of the paragraph, whatever text you want. And then here is the end of the paragraph. Right? Focus on what the document is and don't worry about exactly how the document will be laid out, because different publishers have different style rules. Some like to indent their paragraphs, the first line, others don't. Some like ragged right, others don't, all that sort of thing. But when you're interchanging a document, you should let the publisher pick the style and not worry about this level of detail. Now, when this idea is taken to the web, when you're talking about web pages, you can still use this idea to some extent, right? That is, if all you're presenting is a web page that looks very much like a printed document, this approach is going to work pretty well. And that's pretty much what HTML has stolen from SGML. The idea is let's focus on the content and let's let the browser worry about the details about layout. It'll know how wide the screen is and all that sort of thing. Don't try to sort of overthink it. But there's a downside to this approach. And the downside is we've lost the imperative, right? We've lost the ability to put in details. And sometimes we really want to do that. And to some extent, as we're going to see, although HTML started off very much in this publisher's let's keep things portable mindset. This is really, HTML version 1. Over time, it started to evolve more into this direction, partly because software engineers kept saying, we want to write programs, we want to write programs. We don't want to just write text. All right, but before we get back into the imperative mode, let's do some terminology here. Of HTML. And to some extent, this is taken from SGML, since we've just stolen the good ideas from the publishers. First off, we have the notion of an HTML element. And an element in an HTML document is something that, starts off with kind of a begin symbol, like P for paragraph. This is how you do paragraphs in HTML. And it has a bunch of stuff here. And at the end, it says, okay, our P, in this case, it's a paragraph element, is done. And you'll see that same pattern over and over again, right? You can have, for example, a section and a bunch of stuff in here, and then an end of section. Now, these things here are called tags, right? The P and the section, and these are tags here. You can tell whether or not the tags is marking the start of an element or the end of the element by seeing whether there's a slash right after the open angle bracket. There are some kinds of elements that don't contain anything. And you can mark that something like this. All right. Whoops, I'm sorry. We'll get it right here. This means I'm an element, and this is both the opening and the closing tag. So there's nothing in between, right? So these are called void elements because there's nothing inside them. Now, it's a little bit more complicated than what I've let on, because there's something else you can do with these elements. You can elements can have attributes, and the syntax for an attribute is going to be done something like this. Here's a section with an ID attribute. Introduction. And you can have as many sort of attributes as you like. Right? So you can put as many attributes, and attributes are name value pairs associated with the, the elements and given in the opening tag. The names are, identifiers. So they use lowercase letters and that sort of thing. You can use a few other characters like hyphens in them. They should be distinct. You can't have two attributes both named ID on the same element, because then people couldn't figure out what the ID of that element was. The values can be any string. You can put whatever strings here that you like. So the values can be arbitrary. The names, however, should be identifiers. And what else? Some elements are what are called raw text elements. They're not very common, but they do exist. And a raw text element has inside the element only text, right? Can contain only text. They can't contain other elements, but normally elements can map, can nest. That is, you can have text and other elements sitting in here inside the element. Now, notice that the nesting only occurs inside the elements. Attribute values are just strings, right? You can put, you can't put an element inside here. An attribute value is just going to be, in effect, an array of characters. All right, so what's going on here? I've given you the syntax, but I haven't really given much of the semantics other than having suggestive names like P in section. But there's something else going on here other than sort of what do I mean by BR and all that sort of thing, which is that this is sort of a representation for a tree, right? You can see an entire web page. It'll look something like this, HTML, a whole bunch of stuff, and at the end, /HTML. And there will be things inside here. There'll be, say, a head, and then the end of a head, and then a body, and then the end of a body. And there will be things inside here, right? There'll be, say, an H1, \H1, and then, say, a start of a paragraph, end of paragraph, and so forth and so on. And what this does is it represents a tree. Tree looks like this. I'm an HTML element. I have a head, and I have a body. And in this case, the body has an H1 element and a P element. And there's going to be some text in here, some more text in here. And, there's probably going to be some other stuff in here, say a meta element, whatever. And you can have, other text sort of in between here. There can be maybe some text here, that sort of thing. So you've got a tree where the nodes of the tree are elements, and the leaves of the tree are either text items or in some cases, say, void elements. There could be a BR element here. Let's do that here. BR. Right, so you can have elements with nothing underneath them. They're void. But to some extent, you can think of the elements as being kind of the internal nodes of the tree, except for the void elements. And then the text as being the leaves of the tree. Yes.
So would the interpreter actually like go through a tree and traverse it to output the web page, or does it?
I'll get to that, but that would be that's the simplest way of doing it, right? That is, what the web browser does is it gets the web page, it builds a data structure in its memory that looks like this, and then it sort of walks through this and figures out how to display it. Absolutely. One thing that I've left off here is, well, what about these attributes? Well, you can think of the attributes as being sort of attached to nodes in the tree, right? So if we have a section, I guess I didn't have a section. Well, let's put a section here. Why not? Section. You know, and then ID equals ABC. And we'll put the paragraph inside the section. Why not? So that meant here, I had a section. And underneath that, I had a paragraph, some text here. But associated with the section is this attribute, right? It's not really a subtree. It's that this section has ID equals ABC, right? And that's associated with the element. So the elements have subtrees or subsidiary text, but they also have attributes associated with it. And you can think of them as being sort of advice to the browser or other kinds of information to the browser as to how to display the attribute. I'm sorry, how to display the element, or maybe the relationship between this element and something else in the document. So in some sense, you can think of HTML as just a tree notation. It's a way of taking a beautiful data structure that you've thought in your head and built in memory and shipping it over a wire or over a Wi-Fi connection to another program, which can then take this, you know, byte by byte representation and convert it back into a tree, right? It's a way that we've developed over the years to ship trees, okay? In CS31, you learned about trees as being an important data structure. You learned about a whole bunch of other data structures like stacks and queues and other stuff like that. Well, in the web, trees rule. And to some extent, if you want a different data structure, you build it out of a tree, right? You can implement a stack with a tree, right? It's just a tree with, you know, a bunch of nodes, and you have more nodes if the stack grows and all that sort of thing. So if you need a stack and you want to ship it over the wire, convert it, think about it, representing it as a tree. You can ship it this way and then get the result back. All right. So now there's a problem with this approach. And this problem comes up over and over in sort of software engineering, which is sort of, well, two problems, I should say. The first problem is, what do you do when things go wrong? And the second problem that can occur in particularly in a distributed application is, how do you upgrade? Right? And by upgrade, I mean, you have a fancy new application. It wants to display something new in browsers. It's not a paragraph or a section or anything like that. You have some nice new sort of video feature that there's no HTML element for, right? How do you upgrade, or maybe another way of putting it is update sort of the HTML format? Let's start on problem one first. It's the easier problem. Okay, so what can go wrong? Well, first off, what you can have is a document, here we go, HTML, here's the body. Here's the start of a paragraph. Hello. And then end of body. And then end of HTML. So what happened here is there's no closing tag for this element, right? The nesting is wrong somehow, right? I mean, I suppose it could be maybe we'll see later on something like this at the end, right? So we have sort of improperly nested tags, right? So that's one approach, right? The sender made a mistake and used, in effect, parentheses that don't nest properly, okay? But a more common mistake is the sender just omits the closing bracket entirely. So what should we do in this situation? The long-standing tradition on the internet, this is sort of a mantra of CS 118, right, is be strict in what you generate. That is, when you're sending an HTML document, don't do this because it's confusing and you don't want people to be confused, but be generous in what you accept. So the long-standing tradition in web browsers is to take documents like this in which there's a missing bracket and say, oh, you made a mistake. Oh, I'll just put in a closed paragraph. And where will I put it? The default is put it in the last place it could possibly appear to make the document valid. So we will sort of assume there's a closed paragraph here just before the closed body, because that's the last place you can put it and still generate a valid document. This tradition also has an efficiency advantage, right? That is, if you omit closing brackets whenever possible, such that it makes it valid if you insert the opening bracket at the right time, well, then your document's shorter. Use less network bandwidth and that sort of thing. And for this reason, it's now quite common for HTML documents to look like this, right? We just have a paragraph here, and we'll start up another paragraph here. Okay. And the recipient is supposed to know that paragraph elements cannot contain other paragraph elements, right? Paragraphs can nest other things inside them, but you can't nest a paragraph immediately inside another paragraph. And because the recipient's supposed to know that, the recipient will mentally insert a closed paragraph here, because here's an opening paragraph. And the only way that's going to be valid is if we close this paragraph off first. And the recipient will also, of course, insert a closed paragraph here because we're about to end the body of the thing. So you just see start a paragraph, start a paragraph, start a paragraph, and the recipient figures things out. Yes. Does it violate which? I'm sorry, my ears are not working today. Yeah.
Doesn't that violate like being strict in what you generate?
Oh, yes. So to some extent, this is a mantra, but not everybody buys it, right? But you're absolutely right. And this has been a point of contention in sort of the HTML web community for decades, right? Some people believe this because this is a long-standing internet tradition, but then there's this efficiency argument against it, right? Let the recipient figure it out, right? And so there is that controversy. Yes.
Which like efficiency do you actually gain? Because doesn't there need to be a trade-off with the actual deduction that we need to put a closing tag at the end of that paragraph?
Yeah, part of this is how much does it cost to have smarter clients versus how much does it cost to have cheaper transmission? So it's a question of computational efficiency and transmission efficiency. Part of the argument for saying let's have smarter clients is we can, right? That is, the processors on cell phones and laptops of today are just immensely more powerful than when the web was created. And so we got plenty of CPU time to do this sort of thing. It's really not a CPU time issue. Another part of the argument is we want our browsers to be able to handle these glitches anyway. Because people make mistakes when they're generating web pages. They do it all the time. They don't intend to forget the closed P, they just forget, right? And do we want that to cause the entire application to fall over and die? No. I mean, we want our system to be robust and keep going when there are typos. Since we want that anyway, and we have to have that anyway, let's just use it rather than have it being an exceptional thing. So that's part of the argument. I'm not saying everybody buys this argument, but I'm saying it is a valid argument. Yes. Do we do what? Are we doing compression here? Oh, the assumption I've been making here is that compression is a separate layer. That is, the protocol decides whether or not stuff is compressed. And if it is compressed, then say the entire web page is compressed. We don't have some of it uncompressed and some compressed and switch back and forth. We let the lower level of the HTTP2 protocol deal with it, or HTTP3. So, and I think that's pretty much how everybody does it. All right, other comments on sort of these typos? Yes. In this particular case, the efficiency comes because we don't actually transmit these closed Ps. So the document that is sent over the internet is shorter. And so that's more efficient in terms of transmission overhead, right? It takes less work on all the routers in the meantime, and you get your data fast. Now, it's more work on the client side because it has to mentally interpolate the Ps, but a lot of times the network transmission is really the thing that's your biggest bottleneck. So you'll go to some work to make the network transmission faster. And that's why compression is so popular now on the internet. It's more computational effort on the server and on the client. It contributes to global warming, right? Because we got to compress on the server. That takes CPU cycles. We got to decompress on the client. But it means fewer bits are flowing over the networks, and that saves on global warming. Which is the win depends on various factors, but how shall I say it? The latency advantages of compression often outweigh the disadvantages. The fact that your packets are smaller outweigh the disadvantage that you got to decompress them when you get it. Okay, other comments? Yes. Oh, that's a good point. Usually the tradition, my impression is that if you have a random closing tag that's in the wrong spot, things go awry pretty fast. It's not smart enough to do that, to throw away tags that are present. So the assumption is that if the author put the closing tag in there, the author really meant it, right? It's not the recipient is probably not going to delete it thinking that it's a typo. Yes. Oh yeah, so suppose, for example, the transmission is completely cut off, right? So we get something that looks like this, right? In that case, what most browsers will do is they'll mentally supply all the closing tags necessary at the end of the document and then, display what they got. So you'll see a partial web page truncated of some sort. Yes. Oh, no, 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 no. Suppose, for example, instead of omitting these, suppose by mistake, we put a close HTML here, right? That's a random closing tag. What it's going to assume then is, oops, we forgot to close the P and we forgot to close the body. So it'll mentally insert this, right? And, and then basically all the rest of this stuff, it's going to say, I don't know what to do with this. It'll probably treat it all as a typo, as a syntax error. So if you insert a closing tag by mistake in your document, bad things will happen. Yes.
What if you put
It might ignore it. Yeah, if it sees a closing tag with no corresponding opening tag, is it'll say, I don't know what this is. It'll probably ignore it. Notice that we have to be careful. Well, no, yeah, that's probably what it's going to do. Right? Any other comments? I wanted to mention a very important element that's been in HTML since the beginning, and it's responsible for the W in www, the fact that it's a web. The idea here is that documents, or they're called resources on the web, can point to other documents. So if you are just have some random text somewhere in your document, and you want to make one of the words or phrases clickable, you can turn it into a link by using the A element. A is short for anchor, and to some extent, it's the most important single element in HTML because it has an attribute, href, I guess short for HTML reference, which has as its value a URI, Uniform Resource Indicator, or sometimes called Uniform Resource Locator. Technically, they're different, but I'm not going to go into the difference here. And here you can, list somebody else, right? You can mention, I don't know, let's go to the ECE department. And you see in here the familiar thing that you see at the top of all your browsers, right? So href is the most important attribute of the A element. There are other attributes, but this is the one that you see all the time. And now you can list here inside the A element the text that you want to highlight. Right, so here we have a P element. If I were to draw it as a tree, we have a P element. It has some text. Now is the, and then a period here, but there's an A element here. Underneath that, we have the text time. But the important thing is that the A element has the attribute href equals this URI. Okay. And this is kind of how the web is built. It's how one web page can refer to another. It's even how one web page can refer to part of itself. Question? Oh, this meta element here it's kind of shorthand for meta information about the web page. So you won't see this typically displayed on the screen. The meta information will be sort of information about it. For example, you might have, I don't know, say a link to the author or something like that. Or another bit of meta information might be the data encoding for the current web page. So you can know that it's UTF-8 versus something else. That's sort of information about the web page as opposed to stuff you'd see displayed. Yes. The link tag is meta information about the entire page. You don't see these very often, right? So it might specify, the author or something like that. The A tag, the A element, I should say, is far more common. It's used in the body of the web page, and it's used to point to other parts of the web page. These URIs have a whole syntax of their own, right? So there's the protocol at the start, which is commonly these days HTTPS, and then a colon, and then a domain. So you can say, www.ucla.edu, right? And then a resource, which might be, I don't know, index.html. So this is a resource available at this website. And then you can have other stuff. For example, you can have a sharp sign ID here. And this specifies a particular sort of node within that particular web page, right? So this is a location in that resource. And so, for example, I did mention, I think that you can give identifiers to sections. Well, I'll mention it again. You can have a section, and you can say ID equals, say, intro. Over here, we can say sharp sign intro. And this will tell the browser when it follows this URL, download this resource, parse the HTML in it, look for an element in there that is got the ID intro, and put that element under the user's cursor, so that the user is positioning to the introductory paragraph of that web page rather than to something else. Also, when you're talking about the A element, you can use shorthands. For example, you can take all of this stuff here and delete it. The default resource is the one you're currently looking at. So if you just say href equals sharp intro, I should say, this means this is a reference to the intro section of the current web page, right? So this is a nice shorthand. You don't have to spell out the current web page. Yes?
Is it possible for href to refer to a location or resource that most refers to another href link and follow that link?
Oh, can you have a link to a link here?
Yeah.
That can be done. It's usually done in a different way, though. So what will happen is one of these resources, when you fetch it from the server will say, oh, that's a valid resource name, but you really mean this other resource name. So then you can go and issue another HTTP request to fetch the resource that you really wanted. That's a handy sort of fix, right? I mean, suppose you move a web page from point A to point B, because then you can leave, in effect, a forwarding address from the old web pages. But there's an efficiency downside to that, because now there's 2 round trips between the client and the server to fetch what you want. So, it's controversial as to whether that's a good idea. Sometimes it's worth it, sometimes it's not. All right. Other questions about references or HTTP? I've been talking for too long. Let's take a break. We'll start up at, say, 1:15. All right, let's start up again. So I mentioned two problems before the break. We only talked about one of them, which is what to do if there's mistakes, right? And how the fact that the browsers sort of try to accommodate mistakes sort of led to servers, sending shorter data, sometimes purposely with mistakes and that sort of thing. But a second problem, and a related problem actually, is this is problem 2, how to upgrade the web. And the issue might be something as simple as following. The web might originally have some sort of way of doing a menu, right? And the menu would have choices, right? I'm just making this up, but that's okay. And you can imagine an original set of browsers in which this menu was, pretty stylized. It was sort of a vertical list of choices, and you picked one and you're off to the races. But suppose soon after this, they discovered that there's really a need for two kinds of menus. One in which you make a single choice, and another one where you choose any one of, several out of the choices, right? So one is sort of a radio button choice, right? So called because you pick one, right? And the other one would be sort of a multiple choice, multi-choice, where you can choose, all of them if you want, or choose n, right? Right? And so this original approach assumed, say, the radio button, but you want to have this kind of menu as well. Now, there's one possibility in order to sort of extend, to make this change, is we change our HTML. So we now, for example, add an optional attribute called the menu type. And we say, okay, if you say type equals multi, then it's a multi-choice menu. And if you say type equals radio, it's a single choice. And for backwards compatibility, if you don't specify a type at all, it defaults to radio because that's how we started. Right? So the idea here is that if a server is talking to a new client, it can sort of put a type field here. And if it's talking to an old client that doesn't understand the type field, then the client will be generous about what it accepts. It will see a type field that says, oh, this is. So it will just give you a radio button. At least you'll be able to choose one thing. You'll get some of the functionality of the improved website. I hope this example helps you see some of the problems involved, right? Servers and clients get updated at different times. They will have slightly different versions of the protocol, of the HTML, I should say. And how do you deal with old servers talking to new clients? That's not so bad. But when you have new servers talking to old clients, it's going to be more of an issue. They'll ship out HTML that the old client won't understand. They'll try to interpret as best they can because they're trying to be generous. And it's going to be an issue, right? So how do we do this? Well, here are some choices. Method 0 is just muddle, right? In the way that I described. That is, trust that the clients, when they see stuff they don't understand, will give you a web page that's sort of good enough. Obviously, that's not a very good approach, but it's taken more often than we'd like. Another possibility is that when the client contacts the server, the client tells the server what sort of kind of HTML it can handle, right? So the client request specifies sort of which sort of HTML flavor it understands. Right? So the client says, I understand HTML version 4.2 as part of its request, and the server is programmed to generate a web page using that HTML format, even though it's relatively old, the server has code in it to deal with it. This approach is going to be better than method 0, but it's also a gigantic hassle, because now it means servers get more complicated. They sort of must or I should say support many HTML flavors. You can write code to try to do that, and it can sort of work, but it's a real pain to test. The server authors kind of don't like that at all, right? So a third approach is the other way around. The server, when it responds back to the client, it tells the client which HTML flavor this particular response is, right? So the server specifies the HTML flavor in its response. And then it's up to the client to figure out what to do with that. Okay. And to some extent, under this approach, right, to some extent, the clients have to support multiple versions. Or if they don't support a version at all, they go back to method 0, right? And this is approach 2 is the one that was actually taken in the early web. Okay. And the way that it was done was with a technology that was stolen. Oh, yes, go ahead. Louder, please. Method 0 is you just ignore the problem, okay? And you trust on the internet tradition of being generous in what you're willing to receive, right? So the client and the server disagree about what HTML means. The client gets HTML that it thinks is a typo, or it specifies attributes that it doesn't know what to deal with because they're dealing with different HTML versions. When that happens, the client does the best it can. It ignores attributes it doesn't know what they are. If there's an element that it's never seen before, it puts a question mark on the screen, but it displays everything else. So you just it kind of turns into a bit of a mess, but you can still get work done as long as the fancy new features are sort of not in the way of what you want to do. Yeah. Doesn't it resolve the problem of what? Yeah, and in some sense, this is, how should I say it? It's a little bit better than version 0 in the sense that, if you assume HTML versions are a progression, so each HTML version is an upwards compatible, has new features, but all the old features mean the same thing, then this is kind of the equivalent of this, right? But it turns out HTML isn't that way. Not only do they add features, sometimes they change the meaning of existing features, sometimes they remove features. So in that case, this is going to be better than just this. All right, other comments about this approach? All right, so when we're doing either 1 or 2, the issue comes up, okay, now how do you say which HTML version it is, right? And what was done reasonably early in the development of the web is an attempt to write down what we mean by an HTML version with what is called a document type definition. Or DTD for short. This is taken from HTML, where the idea was sometimes publishers want to interchange books. Sometimes they want to interchange newspaper articles because they're newspaper publishers. Sometimes they want to interchange business letters and all that sort of thing. And each kind of thing you want to print has different needs. And so what they would do is they would have, okay, we have a document type book, a document type newspaper article, and that sort of thing. And what a document type definition does is it lists all the elements and their attributes, allowed sort of attributes and sub-elements, and whether they're void, whether they're raw text, that sort of thing, all of sort of the syntactic properties of elements that would go into a document. And the document type definition would say, okay, for something to be a valid newspaper article, all the elements in our document have to look like this. And a different document type definition would say, okay, for something to be a book, then the elements in a book look like this. You have chapters and subheads and all that sort of thing. And in effect, you can think of a document type definition as being sort of a grammar. I'll put that in quotes. It's not exactly a grammar for a particular document. Okay. So what web designers did is they took this idea and applied it to HTML versions, right? So they came out for a DTD for HTML version 2, that sort of thing, and version 3 and version 4, all that sort of thing. And each one of these DTDs was decided on by the group of vendors and a few users, because the idea is we wanted servers and clients to agree about what HTML meant. And when we added new features like video streams and that sort of thing, we wanted to have a video element and that sort of thing, and that would appear in one of these things. And then we would sort of agree on how to interpret this evolving document set, right? And in fact, one of the things in the DTDs, these DTDs specified whether it's okay to drop the closing tag of an element. That practice became so common that they decided to standardize it, right? Whether the closing tag is optional, right? This became sort of one of the parts of the DTDs. Now, this was an effort that to some extent succeeded, but to some extent it failed. And it failed because the web evolved too rapidly for the standardizers to keep up, right? HTML version 4 came out months or even a year or two after the features that it standardized were already widely used, right? These standards were late. Because to some extent, although they were doing the best they could, committees are slow. Getting consensus takes a while. And to some extent, the consensus was, well, Chromium is is supporting this new element. I guess I better do it now, and I'm not going to wait for 6 months from now. So for that reason, in HTML5, which is the current version of HTML, there's a different approach. Instead of having a standard DTD that's set in stone, at least for this version and that sort of thing, You can think of it as being sort of an evolving standard. They put it on GitHub. They make commits every now and then. And when they make a commit, it's done, right? That new feature is in there, or this change in interpretation is there. It's no longer the old-fashioned wait for n months and vote. There's sort of a committee that's, well, they still have votes internally, but it evolves more rapidly. But to some extent, what's happened here is, you know, our attempt to sort of standardize in the traditional sense has been too slow. There's one other way in which this early element sort of thing failed, which is HTML became very complicated. There's a lot of elements in there, some of which we probably don't need anymore. They're taking some of them away in HTML5. But it's a complicated way to express a pretty simple idea. And that simple idea is we need a way of shipping trees over a wire, right? You can think of it as data structures on wheels. That's really a very powerful idea. HTML sort of does it for a particular kind of tree, that is trees representing documents and web pages. But it was decided, you know, sometime in this process to sort of abstract this notion of representing an attributed tree in text. And that effort is called XML. You can think of XML as short for extensible meta language. But really what this is it's sort of the bare bones for HTML syntax with no semantics. So basically, XML says, here's what the documents look like. Oh, and yes, you can put attributes on them. Right? And you can put stuff inside them, but I'm not going to care what X, Y, Z and what X and ABC mean. That's semantics, and all I want to worry about is syntax. Because XML was semantically independent, and it was designed to work without DTDs, right? You just use the angle bracket notation in the right way. It couldn't do this sort of thing, right? Since there was no DTD to say, oh, it's okay to leave off the closing bracket, XML insisted on always having closing brackets. So in some sense, it's very sort of a simple way to send tree structured data. And if you have a browser, you already have a copy of Firefox or Chrome or something like that, then this browser ought to be trivially able to parse documents like this, because it already has to parse HTML. And you can almost think of this as being a subset of HTML with no semantics. Well, that's an easier job than parsing full HTML. And so the idea of XML was to leverage off the infrastructure that had already been developed to ship web pages into shipping data of any form. So this data is not necessarily a web page. It could be some other data. It could be some payroll element saying, pay Dr. Eggert, it's the first day of the month. Where's his paycheck? That sort of thing. And it doesn't have to be a web page. This effort even went back to try to sort of make HTML saner. There is a variant of HTML called XHTML. And a simple way of describing this is to say it's strict HTML in the sense that it's like HTML, but you can't leave out the closing tags. You have to put them all in because XHTML is valid XML. Right? And This technology is still reasonably widely used. There are competing technologies. It hasn't taken over the world, but it's a way of shipping sort of data across the web. All right. I now want to go back to HTML, though, and talk about a related topic, which is we want to go away from HTML's declarative roots, and we want to make HTML more imperative. We want HTML to be more like a program. And we're going to start off by talking about the document object model. Or DOM for short. And the basic idea of DOM is pretty simple. HTML is a way of shipping trees to the client. DOM is a way of representing those trees, either in the client or the server, right? So this is an object-oriented model for sort of a tree data structure in which the nodes are elements and they have attributes. And, the leaves are text and some other stuff, but commonly text, right? So you can think of that as being a data type. You want to have an object-oriented program look at values of this data type and not only look at these trees, but also manipulate them. You want to be able to read these trees and write these trees and update these trees, right? So it's, for examining and manipulating these trees. And to some extent, object orientation is a natural way of doing this, right? You can think of the element types as corresponding to the object types in your object-oriented language, and you can be off to the races. Originally, DOM, well, and still officially, DOM is intended for any language, for any object-oriented language. In practice, it's most commonly used, of course, with JavaScript. JavaScript is an object-oriented language. You can manipulate your web browser's hashed tree, right, on the client by using the JavaScript binding for DOM. So you can walk into the tree, you can look at the attribute for an element, and then you can go add a different attribute. Or you can remove an element. You can do all of that stuff. Now, there's one other aspect that I suppose I should mention. So we're talking about here about imperative sort of aspects, but we're sort of getting into it gradually, right? DOM itself is not really imperative. It's just a model for representing the declarative structure of your tree. The idea that you have JavaScript that can manipulate it is where imperative starts going in. There's another sort of halfway between imperative and the declarative part of this system called cascading style sheets. Or CSS for short. So here, what we're trying to do is keep the good parts of the declarative approach, just saying what you want, but to separate those declarative things into two major categories, right? So we're trying to separate our declarations into two categories. The first is the actual content. So if it's a paragraph, it's the actual words in the paragraph, right? And the second part is the presentation. how that paragraph looks on the screen when the user tries to read it. And so it's focusing on style, which is another way of putting presentation. And the idea is whenever the browser is trying to render any single word on the screen, it will use a style specified via CSS. And this style basically can come from many different sources. And that's where the word cascading comes from. All right. The style, this presentation can come from, well, first off, you can have sort of user preferences. So when the browser is rendering a word, should we use a 10-point font or 12-point font? Well, the user in their browser might have said, hey, I like 12-point, right? So that can be one source. Or it could come just from the element involved. We have a word, it's in the paragraph. The paragraph will have an attribute, and the attribute will say, I want this paragraph to be set in 10-point font. That's another place that the style can come from. Or it could be not from the paragraph itself, but from an ancestor element in the current DOM, right? An ancestor element. Right? And there's other places that it could come, but I hope this gives you an idea. You have multiple different places where presentation can be affected either by the user directly or by the programmer or that sort of thing. And what cascading style sheets does is it gives a standard for how all these preferences can be sort of combined. What do you do if the user says one thing and the paragraph says another? How those conflicts get resolved, or how you merge seemingly different things like, say, size and font, and then suppose you don't have a font of that current size, what do you do? All that sort of thing. And so cascading style sheets, in effect, attempts to still be mostly declarative, in that you look at the document and it'll say something like paragraph, style equals font size 14 or something like that. And so it still looks somewhat declarative, but the rule for interpreting the style turns into something that's going to be more complicated, and it has to deal with preferences. All right, to some extent, this is about as far as the declarative technology takes us, but it's not enough to do common things you want to do in web applications, right? Yes, you can specify menus in which people make selections and that sort of thing, but you can't specify complicated interactions where you click on the upper left-hand corner of the screen, you see a dancing bear. And if you click on the lower right-hand corner, you see a dancing hippo or something like that. There's just no way you're going to be able to do that. And for that, we actually need code. Various coding technologies have been used in the web world, but of course, JavaScript is by far the most popular. And the idea here is that we have a programming language originally designed for browsers. So the original approach here is that it was embedded in, say, Firefox or whatever. Okay, in the same sense that Emacs Lisp is embedded inside Emacs. It's a programming language designed to be used originally as part of a larger application, and with a particular application in mind, a web browser. All right, but its strength here is that it can be hooked into HTML. So HTML has an element called script, And from the point of view of what we've seen so far, it's just another element. It's just another node in the document object model. It's just another tag that you write in your HTML. But you can put sort of whatever you want. Here's one way to do it. What this means is go fetch from this URL. We're using the shortened version of the URL in which we leave off the protocol name and the web server and all that sort of thing, because it's just assumed that the script is in the same directory as the web page that's referring to it. So go grab this resource off the net. It's got JavaScript in it, and then go run that JavaScript inside the browser. Or you can actually put it in the script itself, right? You can put some actual code. I'll do a really simple one. Right, and what this does is it puts up a little pop-up alert, or whatever JavaScript does on your browser, that says you're running actually code inside the browser. Now, the script gives you a lot more power, and also it makes typos more important. Right? A simple typo would be this. Suppose, here's some quotes. Suppose I forget this quote, what's going to happen? Yes, the JavaScript interpreter will look at this and say, this isn't valid JavaScript code, and won't do anything, right? But you can probably imagine there's more serious typos, like, I don't know, suppose I forget this slash, what's going to happen? Well, in that case, the browser is going to say, this is still JavaScript code, and keep going. And it will feed some HTML into your JavaScript interpreter, which will then try to deal with it, maybe not as nicely as you'd like, right? You're going to have to be much more careful with the JavaScript code, because it's more powerful than sort of the declarative stuff that we've already seen. Also, since JavaScript knows about the DOM, it isn't limited to just doing stuff that's kind of independent of the content. This JavaScript code can reach inside the tree containing the script and change that tree. Yes? Both of these run in the browser. It's just that here, the browser has to fetch another resource off the web. So this is going to be a heavyweight operation, right? And if you have a really small amount of code, you'll probably use this form instead, because that way you don't have to do two fetches. This might be useful if it's something big or something you want to refer to commonly. And if it's something small, you probably just do it inline. All right. So, basically, in order to use this stuff, you're going to need to learn JavaScript and program it. And by now, I hope you're good enough at picking up new software technologies that I don't have to tell you much about JavaScript and how it works, which is a good thing since this lecture has just about finished. All right, so just to remind you, we have a midterm coming up next lecture. It's in lecture. It's open book and open notes, but closed computer, right? So no laptops or cell phones or digital watches or anything like that. You've already seen drafts of old versions, I hope, so you know what the style is. And please come.